taking the same, just taking one sample and finding out the average. So this was said to be the better example, right? Now in the k-fold cross validation, we divide our data set into k power portions. We use k minus 1 portions for training and the kth one for testing, and then we leave one out and use others for training and then for testing. So that's how the k-fold cross validation goes. Any confusion up to this point? Any confusion up to this point? Any confusion up to this point? Okay.
No, ma'am.
Okay. Now the next is leave one out cross validation. Now in this method, in this technique, all of the data except one record is used for training and one record is used for testing. I think I told you this also briefly, and the average is the entire data is used for training and testing. The error rate of the model is the average of the error rate of each iteration. This gets too compute intensive because the amount of training, the number of times the training is to be done. So I'm not saying that this one training means one iteration, right? So you can understand that what is the amount of effort that will be required. So this is one training instance, right? And in this training instance, you will have suppose 100 iterations, right? So this 100 iteration required in one, while the first instance is being done, then second instance, and so on. So in this case, what happens that the effort required is very large. This is an okay approach when you have less training data, because this will help us. Uh, uh, this will actually facilitate us because the testing data we don't have to keep apart. We don't have to keep separately. It is just one instance which is kept separately, which is required to which will be required for the testing later on. So this can be a good approach when you have a less training data, and you can leave one instance out and others can be used for training, repeating this n number of times and taking out the average of all the errors, and finally that becomes your uh, average error, right? Now, random subsampling in this technique, multiple set of data are randomly chosen from the data set and combined to form a data set. The remaining data forms the training data set. Now, here we can see that these are the random samples which are collected, and this becomes the test, and whatever is left is used for training. And similarly, we do it for second time, we do it for third time, and so on. How is it different than k-fold test validation? It is different from k-fold validation because in k-fold validation, the same data set is divided into k portions, and hence this portion remains unchanged. Whereas in this random subsampling, you take random data and you are allowed to repeat that choices also. So in experiment one, so this it may happen that this particular data item is never participating in training, rather it is all the time picked up for testing, right? So this is randomizing the process, and this is also not a bad idea. This also works well, right? So this strategy is also implemented in Python, and you can easily see that you can choose randomly as training and testing. Repeat your experimentation n number of times. Uh, there's a lot of background noise you hear.
No, ma'am.
Hello, yeah, everybody there listening? I'm
Yes,
online.
ma'am.
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, okay. Say something in between so that I know that you're there, right? Okay. So you can repeat this n number of times. So this entire training can be repeated n number of times, and the average error becomes the final error, right? So the error rate of the model is the average of the error rate of each iteration. Iteration here we are calling as this, but every training session will also need iterations within, right? So not to confuse you by calling this also as iteration and this also, and within that training session also any iterations if it is a gradient descent. So we can use that this is the first training session. This is the second training session. This is the third training session. Okay, just to differentiate the terminology. Right now, there are techniques in which I'm able to see the yes. In bootstrapping, in this technique, the training data set is randomly selected with replacement. Now you can see here that this is your complete data set x1, x2, x3, x4, and x5, right? When we selected experiment 1 for experiment 1, you can see this x3 is appearing more than once, right? It is rather 3 times, okay? So in this technique, the training data set is randomly selected with replacement, right? So in bootstrapping, the training data is selected with replacement. So in random selection, it is without replacement. In bootstrapping, this is with replacement. The remaining examples that were not selected for training are used for testing. So randomly we select data items here, the instances here, and these are used as a training set and these are used as a test set, and then whatever is remaining works as a testing set and this becomes the training set, right? The error rate is or the model is the average of error rate of each iteration. I'll repeat again that iteration means all the sessions, training sessions, and the following diagram represent the same. So you can see here that the same data set. So you can see here X4 is being selected 4 times, and here the test set is there are 3 test sets. So this works again. This is a good idea when you have less training data, you have less training data, and it is not possible to divide it into 4 folds, equal folds, and then keep just one fold apart, or even random selection. If I'm saying that random selection and for training and testing, we are saying that 25 and 75, then keeping this 25 percentage aside would lead to even lesser number of training data set, and therefore this may be a good idea to select n number of elements from your data set randomly without with replacement, so that that actually uh, eliminates the challenge of small data set, okay, or rather helps in addressing that challenge, okay. Okay, this we have done, all these we have done, we did, and now the next topic that we have to do under this area is
Ma'am, I had a question.
Hanji Piche, please.
Ma'am, when we use bootstrapping with the replacement,
Hmm.
uh, so we are basically using like we have repeated instance of the same record in both the training and testing set, right?
No, not in training and testing set. Within training, we have the repeated record, not in. So you can see here x3, x1, x3, x3, x5, right? So x3 is gone, x1 is gone, and x5 is gone. And what is remaining is x2 and x4. So x2 and x4. So this is your test set and this is your training set. So with replacement means when you are preparing your training data set for your first go, you are selecting randomly with replacement, and whatever is remaining is your test set. Am I clear?
Yes, ma'am.
Okay. So we have done this. Um, okay. Yes. Now we will talk about ensemble methods for increasing the accuracy, right? So this is one more topic. As I told you, we used to do it after 1 or 2 training algorithms, 1 or 2 machine learning algorithms, but I intentionally took it just after regression and logistic regression so that you just get a taste of it. And this is not a very difficult topic. This is a very simple topic to understand, and you are going to use it in every classification algorithm, right? So in the labs also, when I'm conducting the labs, we are going to use different metrics. So this ensemble method may not be used immediately. It may come a little later, but because this is part of this this particular topic that we are doing, so I'll cover it now, right? Now, sometimes what happens that just one model, right? So the very common approach that we have seen is that we have a training data, we initialize a model, we train the model, and the then trained model is being used for testing and validation using different metric, and then this trained model is deployed for real life applications, right? So this is a common cycle of any machine learning algorithm, right? We have data, we identify an appropriate model, we train the model, the trained model is being tested using different metrics that we have just studied, accuracy, sensitivity, specificity, depending upon your requirement, depending upon your cost of misclassification, and so on. Once we are satisfied with everything, then we deploy that model for the real life application, right? Now, there can be some cases when your one model is not good enough for classifying, right? So I go to one doctor and I'm not very happy with that one doctor, so I want to go for the second opinion, right? So what we do, we use a combination of models to increase the accuracy, right? So we we visit different doctors and we take their opinion that what is your say about this particular problem. So we use combination or a set of doctors for increasing the accuracy. Now combines a series of k-learn models M1, M2 up to Mk with the aim of creating an improved model which is N star. So using ensemble methods, we create a combination of different models which is supposed to be better performing better than individually each of them, right? The most common methods, the popular ensemble methods are bagging, boosting, and ensemble methods, right? So bagging is averaging the prediction over a collection of classifiers. So it is like asking everybody that what is your opinion, what is your opinion, what is your opinion, and taking the best or taking the maximum votes. That's the bagging. Boosting is we visit one doctor, we understand our problem. In discussion with them, we have a better understanding, and then we go to another doctor, and then he may be a specialist or somebody, and we talk to him, and we get even better idea. And then when we go to the third doctor with the improved information, right? So that's what is boosting. Ensemble is combining heterogeneous classifier, right? So these are the three methods. We will see each of them in detail, right? So bagging, in bagging, what we do, we analogy is diagnosis based on multiple doctors or majority vote, right? So, given a set D of D tuples at each iteration I, our training set Di of D tuple is sampled with replacement from D, that is bootstrapping method, right? This is bootstrapping method. A classifier model Mi is learned for each training set Di. Classification में क्या करेंगे? Classify an unknown sample X. Each classifier MI returns its class prediction. The backed classifier N star counts the votes and assigns the class with the most votes to X. So what we are saying that we have more than 9 classifiers. So we have 3 models, right? Model 1, model 2, model 3, model 4. We have data set. We select the data set. Now you understand where is bootstrapping used. We select the data items with, it's impossible to divide it into M portions, right? We don't have that large data set. So with replacement, we select the data set for training, we select it for training, okay? Train them individually. For any new instance, we ask this trained model, we ask this trained model, this trained model, and this trained model. And there is a new model here which is going to aggregate the results by all the three, which is known as N star, right? So we are saying, given set D of D top, what at each iteration I, the dataset Di of D tuple is sampled with replacement. A classifier model Mi, so M1, M2 is learned for each training set Di. Classify an unknown sample X. Each classifier Mi returns its prediction. So इसने कहा yes, इसने कहा no, इसने भी no और इसने भी no. right? M star counts the vote and assign the class with most votes. So because this is the M star, it is going to count the vote and it gives an answer no, right? So prediction can be applied to the prediction of a continuous value by taking the average value of each prediction for given. So if suppose this is a regression type of problem where or suppose this is a probability, so average can be taken out. So suppose the probability of this model, even if this was a binary classification, this gives a probability of zero point 0.7, this gives a probability of zero point 0.2, this gives zero point 0.9, this gives zero point 0.5. You take the average of this, and according to that, the output can be taken out. So it is possible that we can, if you are getting a numerical value, you can take the average, and that can work as an output, right? Accuracy is usually better than the simple classifier. For noise data, not considerably worse. Why it is not worse in the noise data? For the reason that averaging always eliminates noise, effect of noise. Okay, averaging will always affect. जैसे मूविंग एवरेज होता है, आपके पास एक ग्राफ है ना, वो ग्राफ में ऐसे जिटर्स हैं, है ना? अगर आप इसका मूविंग एवरेज लें, यू नो व्हाट इज मूविंग एवरेज? यू नो व्हाट इज मूविंग एवरेज?
No, ma'am.
नो. सो व्हाट इज मूविंग एवरेज? आप हर एक वैल्यू के उसके पिछले 5 वैल्यू के एवरेज से आप उसको रिप्लेस कर रहे हैं, है ना? तो whatever is the value here is average of previous 5. Whatever is the value next is the value of the previous 5, and so on. So value at 6th is the average of 1 to 5. Value at 7th is the average of 2 to 6, and so on. And that's how you स्मूदन द कर्व. तो अगर आपके पास कोई प्लॉट आया है, उस प्लॉट में बहुत सारे जिटर्स हैं, तो जिटर को रिमूव करने का दैट्स अ वेरी वेरी कॉमन टेक्निक which is known as moving average, which is also done in case of image processing, in case of signal processing, so many places, right? So moving average is a very common technique which is used throughout for averaging, for removing the randomness in the data, right? So whenever we are taking the average value, that also removes the randomness which is caused due to a noise in the data. So this noise can be removed by taking the average of all the 5 or 6 classifiers that we have taken. Okay, right. So this is what is known as bagging, bootstrap aggregation, using bootstrap aggregation. You can have different techniques. This is just the concept we are studying. You can think of your own innovative way of doing it. Nobody is going to stop you from doing that, right? I want to take more weightage of M1, less weightage of M3, and so on, depending upon their accuracy, previous accuracy. That's possible. Okay. Now boosting, yeah, boosting analogy. Consult several doctors based on a combination of weighted diagnosis, right? Weight assigned based on the previous diagnosis accuracy. So how does it work? So the weights are reassigned to each tuple, training tuple. A series of K classifier is iteratively learned. Now you can see here a series. Okay, please pay attention to this word. A series of K classifier is iteratively learned. After a classifier MI is learned, the weights are updated to allow the subsequent classifier MI plus 1 to pay more attention to the training tuple that were misclassified by MI. Just a minute. Okay. Now the final M star combines the vote for each individual classifier, where the weight of each classifier vote is a function of its accuracy. Boosting algorithm can be extended for. So, for example, you can see here using this diagram, it is quite simple that in case of bagging, you have the parallel models, model 1, model 2, model 3. You divide your data set into for model 1, for model 2, and up to model n. You train them independently, and then when you have to take a decision, you give the same instance to all, aggregate their outcomes or their decisions, and then that becomes your final outcome, right? In case of boosting, as you can see, it is series, right? So the first model is trained, right? And the initially the weight of every instance is same, right? Every instance is same. Later on, the weight of every instance is updated based on that how good or bad this model is performing. So suppose this model has been given 10 instances as an input, right? 10 instances as an input. It gave a correct answer for this, incorrect answer for this, correct for this, incorrect for this, incorrect for this. So what it is saying to the next model that please pay attention on these incorrect classification because I'm not able to handle it, right? Because I'm not able to handle it, so you please pay more attention to this. So they are explicitly marked as or given higher weights so that learning model 2 can pay more attention to what model 1 could not do, right? So the weights are updated. I hope I have that algorithm also. So this is although at a boost, but it is similar to that. They the weights are updated, right? Weights are updated based on the error. So this is not exactly what the update algorithm should be. This is for error boost. Yes. So what it is saying that after classifier MI is learned, the weights are updated to allow the subsequent classifier to pay more attention to the training tuples that were misclassified by MI. है ना? ट्रेनिंग एरर भी ऐसा तो नहीं जीरो होता है even if we have used 100 data items for training, I give the same 100 for classification without the answers. I'm not going to get all answers correct, even if the same data set has been used for training, right? That's what is known as the training error, right? So the training data pe hi jo error hai, that can always be considered that in spite of the fact that the same data set was being used for the training as well, the same data sets are misclassified, or even in that testing data, if they are misclassified, those tuples are being given higher weights in comparison to the tuples which were correctly classified by MI because the ith classifier is able to handle all the data items of that type or that particular data items or is ready to classify that particular instance but is not ready to classify the instances which are misclassified, right? So which is given ahead, which is forwarded ahead with the updated weight, and these weights are being updated after every stage. So I hope this diagram makes all the discussion more clear. Uh, any comments from anyone? Yes, please.
Ma'am, the time taken by boosting, it will always be much more than what bagging takes because it's a sequential process and we cannot paralyze it.
Yes, that is true. That is true. Yeah, it's a
So,
sequential process.
so if we have a very big data set,
Hmm.
so then can we say that it's not means we should not be using boosting.
Usually in machine learning algorithm, although training time is a parameter, but is not that important parameter in comparison to the accuracy because
Okay.
training is done only once, right? It's not every day's job, right? So if at all, at the cost of more training time, if the accuracy delivered is higher, it is okay. It is worth the investment, isn't it? Because we train the
And
model
if it
once.
is some
Yes, please.
If, for example, if we are doing some real-time kind of prediction, so where the input data set keeps on growing,
Hmm.
so then how do we address that in that case?
Yeah, that is known as active learning. That is known as active learning. In the scenarios which we are studying right now, they're not active learning techniques. In these techniques, the conventional form of learning is that we have the entire data set before we actually deploy the system, and we are not updating it once it is deployed. Okay, so that's not active learning. So what you are saying is that your data set is growing, and the way a human being updates itself every day. It's not that we go to school and we learn, and then once we are out of the school we don't learn, right? We learn every day. So that's what is termed as active learning. But in these models, once it is deployed, we are not updating anything. We are not updating the models once deployed. They are different learning. It's a different learning scenario where there's a term which is known as active learning, and we do update periodically, saying that whatever were the instances which were misclassified are recorded, and then this again the training scenario is executed, and the weights are updated. So that also happens, but not in this conventional method that I'm talking about. Okay.
Okay. Okay. Okay. Thank you.
Anybody else has any questions? I hope this diagram makes things much more clearer in comparison to the algorithms. Yes. Um, I'll encourage people to speak out so that I understand that what's the scenario, how well you have understood. Hmm? No? Okay.
Yes, ma'am, understood.
Yeah, okay. Now the other is known as data boost. And now given a set of D class label tuples, we will have this. Initially, all the weights of tuples are set as same, 1 upon D, and generate K classifiers in K rounds at round I. Tuple D are sampled with replacement to form a training data set DI. Each tuple's chance of being selected is based on its weight, right? So weights. A classification model MI is delivered from DI. Its error rate is calculated using DI as the data. So the same training set, right? The classification model MI is delivered from DI, which is the training data set. Its error is calculated using DI. So up to now in the labs also what we have done is we are training data and testing data set is separate, right? But there we are trying to understand that how good your system is going to perform in the real life scenario. When we are trying to build an AdaBoost filter, we are trying to find out that what are the problem areas or what are the pain areas, right? So for that, its error rate is calculated using DI as the test set, right? If a tuple is misclassified, its weights is increased, and otherwise it is decreased, right? So error rate xi is the misclassification error of tuple xj. So misclassification error of mi error rate is the sum of the weights of the misclassified tuples. Okay. So jth tuple, if the error is true, if the error is true, so this becomes 1. If the error is not there, then this becomes 0, right? So you keep on adding to the previous weight. So wj into 0 and wj into 1. Okay, so that's how you get an error. The weight of a classifier mi is log of 1 minus error of mi divided by error of mi. So this is how you are calculating the error, and this is how you are updating the weight of every instance, or calculating rather the error of every mi. And the penalty for misclassifying a highly weighted uh, tuple is higher in comparison to a less weighted tuple, है ना? सबका weight जो है 1/n है. अगर आपने किसी ऐसे इंस्टेंस को मिसक्लासिफाई किया जिसका वेट बहुत ज़्यादा है, तो वो ज़्यादा काउंट होगा इन कंपैरिजन टू जिसका वेट कम है. So if suppose there is a tuple which is being misclassified a number of times, that becomes crucial, right? That instance becomes crucial. Okay. Okay, now this is random forest. A random forest is a very common tree technique, and we are going to study it in detail after we are done with tree. Okay, trees or decision trees. Okay, and now each classifier in an ensemble is a decision tree, which is going to be our next topic. Classifier and is generated using a random selection of attributes at each node to determine the split. During classification, each tree votes and the most popular class is returned. So what happens that there are multiple trees, okay, and each is trained using random set of attributes. Please see here random selection of attributes. It is not random selection of instances, okay. Here I am talking about attribute as in columns. तो अगर आपके पास 20 कॉलम्स हैं 20 कॉलम्स हैं तो इसमें से रैंडमली कोई भी और ये क्लास एट्रीब्यूट है आपका ठीक है तो 20 में से आपने कोई भी 5 को रैंडमली सेलेक्ट कर लिया each classifier in ensemble is a decision tree classifier and is generated using a random selection of attributes तो इसमें से आपने कोई भी 5 कॉलम्स ले लिए एट ईच नोड टू डिटरमाइन द स्प्लिट ये स्प्लिट क्या होता है ये आपको बताएंगे आप नेक्स्ट टॉपिक ठीक है ड्यूरिंग क्लासिफिकेशन ईच ट्री votes and the most popular class is return right so this is what is known as a random forest technique which I'm going to take decision tree as the next topic which we are going to start today during the classification each tree votes and the most popular class is returned okay so we are going to do this in more details. So here the difference is that all the models are of the same type. So you have tree 1 here, you have tree 2 here, tree 3 here, tree 4 here, and each tree is being run or being is being trained using different models, and this this model is different sorry attributes and then votes of each model is taken and finally whichever is the majority becomes the class okay 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 so this is one example which we have done. Do you want to do an example about how to solve a problem using this? Or I think you can handle it yourself. Okay. If you have any trouble, you can please let me know later on. So we are done. We are done with this topic. Do you have any trouble in this topic? If not, I'll start the next topic, which is decision tree. Okay. So do you see the screen I'm showing you here? Do you see the screen?
Yes, ma'am.
Yes. How many of you have heard about decision tree and how many of you have implemented decision tree at any point of time? Hmm?
Yes, ma'am. We heard about it.
Yes, anyone please?
I've heard about it but not implemented.
Hmm? Heard about
I've
it, but okay, no problem. और कोई?
Yes, ma'am.
हाँ, आपने अग्रता आप में से उस दिन फ्राइडे को काफी कम लोग लेक्चर अटेंड किए क्यों एनी रीजन फॉर दैट एनी रीजन
On
फॉर दैट
Friday
फ्राइडे
there was
को
a lecture. Friday there was a lecture.
Acha, file. No, I think I did not forward you that. There is a Nirma University and Binghamton University lecture series going on. And in that, there is one faculty from Binghamton University who delivers the session and one from Nirma. So I asked all of you to participate in that, and I saw not so many people participating. Okay, please take full advantage of all the things which are happening around and be updated. Okay. Right. So, what is a decision tree? A decision tree is a model, is a learning model, which is the output of a decision tree looks like this. And you take a decision based on this. For example, are your parents visiting? If yes, then you plan to go to cinema. If no, then you look into the weather. That if it is sunny, then you play tennis. If it is windy, you work on this. If it is rainy, you stay home. Right? So if they are visiting, then surely you go to the cinema, or if no, then you do things like this. So basically, from a data set, this is one of the most simple to understand technique, which is termed as a decision tree, with a very small amount of mathematics coming in this particular topic. Um, Neural network is a lot of mathematics, so I'll take that topic immediately after decision tree, because I think I'll be able to finish decision tree in in these three sessions which are before Diwali, or maybe I'll need one more or two. That's it. Okay. Right. So this is an outcome. This is what is the final output of a decision tree. Okay. So your data set would look like this. I'll come to it. The data set would look like this, okay, where you have the instances, you have the attribute 1, you have attribute 2, you have attribute 3, you have attribute 4, and this is your class attribute, right? This is your class attribute. So if based on these four attributes, you decide that whether you want to play tennis or not. Now, as I've always repeated, that machine learning is all about going from specific to generic, right? So these are the specific instances, and we are trying to go to a general approach, right? Um, so we want to generalize that what happens when do I play tennis and when do I not play tennis. So I want to make a chart, or suppose there is a bank manager, he needs a decision chart and want to take a decision based on that decision tree. That if somebody comes who is more than 75 age, then maybe deny him the loan. So if the age is more than 75, then deny the loan. And if it is less than 75, then you can think about it. Then you have to see that what is the asset, and if the asset is zero, then you say no. If the asset is good enough, then you see that he has property, he has a permanent job or not. If the job is there, then you see the salary, and then finally you say yes. If this is the case, then yes or no, and so on, right? So basically, if you see, you want an output like this based on this, right? So you have a data set like this, and I am interested in finding out a decision making capability like this, which can help me in taking up a call. Okay, is that clear? So what is a decision tree and how does it look like? Okay, okay. Right. Now, the science behind it is that um, that there's something which is known as randomness in the data, right? Now, that randomness in data can be measured using entropy. Okay. Have you heard about entropy? Any of you have heard about entropy? Word entropy? Anyone of you have heard about the word entropy?
Yes, ma'am.
Okay, what is that according to
It
your understanding?
it is basically a measure of randomness.
Yes, and where have we used it in computer engineering? Entropy एक आपने chemistry में पढ़ा होगा, entropy of gases, है ना? शायद 11th-12th में कभी पढ़ते हैं ना एंट्रोपी ऑफ गैसेस।
Yes, ma'am.
Yes, ma'am.
है ना, वो तो याद है। एंट्रोपी कंप्यूटर साइंस में कब पढ़ा है?
Ma'am, once in the machine learning course itself in the bachelor's.
ओके, अदर देन दैट इंफॉर्मेशन थ्योरी में नहीं पढ़ा है? या इंक्रिप्शन में पढ़ा होगा? कम्युनिकेशन टेक्निक्स नहीं पढ़ा है आप लोगों ने? नेटवर्क्स, कंप्यूटर नेटवर्क्स नहीं? कम ऑन, दैट्स
Yes, ma'am. We have
physical
studied.
in physical layer encoding techniques we study, है ना? So in I
Ma'am,
think
in data and ma'am, in data compression also we have
yes,
learned.
that's what I'm saying. Information theory, data compression, everywhere you study, it has got a huge application, right? So entropy measures the impurity of an arbitrary collection of examples, right? So it tries to find out that what is the impurity? What is a pure data? Pure data is that if we have two classes, so let us take our simple scenario when you have a class value and all of them has a value yes, has got a value yes, right? If everything is yes, then this is an absolutely pure data, right? This is an absolutely pure data. If you have 80 percentage of yes and only 20 percentage is no, then also this is relatively pure data because there is one element whose probability is higher than the other element. If you have absolutely 50-50 percentage of the data, then the randomness in the data is maximum, isn't it? Then the randomness in the data is maximum. Probability of finding a yes and probability of finding no is same. So it is an absolutely random scenario. If had it been 80 percentage or 90 and 10, then the probability of finding one instance is much more in comparison to probability of finding out the other type of data, right? So as we said, minimum number of bit information needed to encode the classification of an arbitrary member of collection S. So this is how we are going to use it. How do we measure entropy? We measure entropy of the data set where S is going to be used for data set. For the data set, Pi is the proportion of S belonging to class I. So if there are two classes, then summation of, rather I'll not write summation, it is minus probability of yes log of probability of yes to the base 2 minus probability of no log to the base 10 probability of no. So we'll find out what is the probability of yes, we'll find out what is the probability of no, take the log of it and add both the things. So that gives us the total entropy of the data set. Yes. Am I clear? Am I clear?
Yes, ma'am.
Yeah. And why do we need anything which is random, the measure of randomness? Why do we need? So we need to know the measure of randomness so that I can evaluate, okay, so what will be your criteria for decision tree? My criteria for decision tree is going to be that which is most important for me, right? Or which is going to make picture clear. Elimination rule क्या होता है? Which is going to make the picture more clear. So suppose you want to decide that what do you want to wear today. So the first question is, are you going to your work or not, right? So if you're going for work, things are sorted out. You have some pair which you are wearing for work and you decide and you go ahead. Now, so that's your first criteria. The second is, are you going for work? No. So no, then comes the other questions. If not for work, then where, right? And then you decide based on which place you're going, whom you're going to meet, what is the weather, and so on, right? So you're usually the deciding factor is something that makes your picture clearer, right? And how do you measure that what is clear and what is not clear is being measured by entropy. What was the clutterness before and how uncluttered the situation is after you have evaluated our criteria, right? So that is how you take a decision. So we try to measure that what is the randomness in the data at the beginning, and then we will evaluate that if I look into this parameter, how clearer my scenario is. If I look into this scenario, how clearer my scenario is going to be, and third parameter and fourth, and then we try to see that which is making my scenario most clearer, and that becomes my primary deciding factor. Am I clear? Am I clear?
Yes, ma'am.
Okay, so we will do the methodology, the concept I explained to you. We will do the methodology and the entire approach in our next class. I'm sure, so in the next class, and that is tomorrow, we'll be able to finish the at least 2 approaches of decision tree, and I think we'll be done with 1 practice as well. Okay. So see you tomorrow then. Anything else, any questions you have, you can ask me, or else we can wind up the session now. Any questions? Any questions you have?
Ma'am, I have one question in bootstrapping. So, for example, if we take a repeated sample in our training data set, doesn't it induce any sort of bias?
No. Why would it add a bias?
Ma'am, because say, for example, if we have one of the training sets that is,
You feel that that will make bias as in imbalancing the data, you mean to say?
yes, ma'am, something like that. I mean, the model sort of, I don't know, it gets trained in a way where it recognizes some sort of samples and it fails to recognize the other sort of samples.
What is the probability of a sample or instance being picked up? So if you have 1,000 of them, what is the probability that the same instance would be picked up more than once or more than twice? What is the probability? Hardly anything, right? So if there are, suppose 100, even 100 training data samples, right, the same instance being picked up more than once is 1 by 100 into 1 by 100. More than 3 times is 1 by 100 into 1 by 100 into 1 by 100. It is very, very less. Isn't it?
Yes, ma'am.
उसकी probability बहुत कम होती है, पर इससे हमारा जो randomness है, हमारा जो pool है, वो बहुत बड़ा हो जाता है. और less care has to be taken while selecting the data, है ना? तो उससे बहुत फर्क, मतलब जो फैक्टर आप कह रहे हैं, अभी तो हमने सिर्फ 5 एग्जाम्पल लिए, उसमें हमने x4 को 4 बार लिख दिया, तो आपका क्वेश्चन बिल्कुल जेन्युइन है. What you're asking, this question is coming because of the example that I've taken. But when imagine your data set being very large, isn't it?
Yes, ma'am. So so if we take a suitable sampling method, then this is a problem that will not occur, right?
So yeah, this will not happen. Yes. Okay.
Yes, ma'am. Understood.
Yeah. Okay. So we can